Hey Kev, check out my television setup. Hey, I can now watch all my video lectures at once, and if I put them in two times the speed, I get them done in like 2 or 3 hours, and then it sort of totally leaves me ready to be sort of man of leisure, and I can spend all my time playing football and stuff. Hey,
Sounds awesome, Jono.
yeah, well, it's mostly boring stuff, right? The odd snippet of useful information here and there, but that quantum mechanics course is actually turning out to be pretty entertaining.
Yeah, you reckon?
Yeah, the dude who teaches it, he used to have this YouTube channel where he used to do like physics demos 11 years ago or something. And he said he stopped doing it because, it kind of lost its edge and every man and his dog was putting that stuff up. But he reckons he wants to make a comeback now. He was saying, fair dinkum, he wants to do the craziest physics demonstration in human history.
What does he have in mind, Jono?
Well, he was calling for volunteers from the class to, take some special Doge coins or something and go up into space with them.
Doge? To the moon?
Well, I said that too, like, what, to the moon? And he was like, nah, to the moon's so 2019. I want to go somewhere out there, like Alpha Centauri. And I had to think about it. I thought, I'd put my hand up for that. It sounds fully sick, like fly around a galaxy, visit some planets, maybe get some punch on with some aliens, do the demo, come home again.
Sounds risky, Jono.
Oh, he assures me it's totally safe and says, definitely be back in time for exams. Sounds great. What could go wrong? Yeah, Houston, Schrodinger's cat here. I reckon we're good for the ride. You can just press the button whenever you're ready, mate.
Copy that, Schrodinger's cat. We are go for launch.
T-minus 15, stand by for terminal count. 10, 9, 8,
Side booster ignition.
6, 5, 4, 3, 2,
Today's lecture, I want to shift topics a little bit. I want to get away from a very tight focus on a single quantum spin and start looking at what happens when we have pairs of quantum spins that can interact with each other. Where we're going across the next two lectures is to start taking a first look at a concept called entanglement that's kind of foundational to technologies like quantum computation and quantum information science. Having taught quantum mechanics for about a decade or so, I've really sort of come to hate the sort of spooky weirdness that people try to hang around entanglement and ideas like wave-particle duality and so forth. And I dislike it because it tends to be misleading and send people in one of two directions. They either decide, ooh, this is weird and spooky, so I'll never understand it, so I won't bother trying. Or what they do is go that it's some magical panacea that enables quantum mechanics to be special and somehow do all sorts of things that it just totally cannot do. And both of those are bad directions to go if you actually want to work in the subject. It's not true that you can't be rational about these things, and it's not true that there's anything truly spooky or weird about this subject either. At first it's unusual, but once you sort of stick around for a while, you sort of come to grips and you feel perfectly okay with it. So I'll keep my views on wave-particle duality for elsewhere, but some of what I want to do in these two lectures is actually try and demystify this idea of entanglement a little bit. And so the way I want to approach this is, first I'm going to build a little bit of a mathematical framework for how we handle pairs of quantum systems, just so that I can connect the idea of Hilbert spaces and notation that we had for one spin and sort of ease gently into the way we handle state spaces or Hilbert spaces for pairs of systems. Then what I want to do is to finish off the first half of this lecture, I actually want to look at classical correlation. It's a thing that you really don't get taught much about in your physics courses. It usually appears, somewhere way back in your maths courses on probability and statistics. And as undergraduates, even whether or not you've done those courses, it's often difficult to take that concept from somewhere in a different course and actually logically hook it into something that's a very new concept like entanglement. Having dealt with that, because it gives us a nice foundation to work on, in the second half, what I want to do is introduce some sort of two spin states. And those will be a product state, which is a good example of a non-entangled state, and then a singlet state, which is sort of what we consider to be a maximally entangled state. And that will set us up for the next lecture where we look a bit more detail at what happens with the quantum mechanics of entangled states. Okay, so to get rolling, what we're going to have is two quantum spins. I could call them system A and system B and drive you nuts trying to do A and B all the way through, and me sometimes even going B instead of A and getting myself mixed up. Thankfully, the people who started working in the early stages of quantum computation found the same problem, and they decided to solve it by introducing characters to represent the various parts of our systems. So what we have instead of system A and system B is Alice and Bob. The Alice and Bob I have here might be a little too fairy tale for undergraduates. So maybe if you're more on the bad side, you might like to see Alice and Bob like this. Or I actually kind of like to have, since we're in a quantum mechanics course, superpositions. So I'm going to consider my Alice and Bob to be superposition of good and bad for the way through this lecture. Okay, and so this is how we'll refer to our two systems. Alice will have one, we'll call it Alice. Bob will have another, we'll call it Bob. And later on, you'll see we'll introduce a few other characters along the way. And this kind of keeps it fun and easy to work out what's going on here. Okay, so what I want to do is just start with some notation. And the best way to start is actually to give Alice and Bob different quantum systems, because it kind of highlights how the mathematical structure goes together. So what I'm going to do is I'm going to take Alice and I'm going to give her a quantum coin. And the reason why I want to do a coin rather than a spin at the moment, you know that they're kind of equivalent, is that it makes life a little bit easier when I talk about classical correlations at the end of this first half. Some of the students used to complain in the past about me using Coiny because they couldn't, because they got a bit confused between coin and Coiny. And I've decided to update my notes this year. So in the interest of getting modern, since Kanye is kind of over now, we're going to go to Dogecoin. So Alice is going to have like a quantum coin. And she's going to have two basis states, heads and tails, which is our equivalent of our up and down. And she can set this coin into a superposition of heads and tails with prefactors that enable that to be normalized alpha H and alpha T. Okay. And if you want to, from a classical perspective, you can imagine when the coin's spinning in the air, it's in some superposition of the two states, because ultimately we're going to measure it and work out which of the two states we get. What we're going to do is give Bob a quantum dice. This time we'll give him a fluffy one to match his hair. And as you remember from way back when we talked about visualization in quantum mechanics, our quantum dice has 6 basis states. 1, 2, 3, 4, 5, 6. What I'm going to do in order to distinguish between the two systems from a sort of a bracket notation perspective is I'm going to keep Alice with the usual angle brackets. And if you want to remember that really easily, the A has a sort of sharp angles to it, and that gives you a sharp angle at the front. And then for Bob, I'm going to give him curly brackets, either to match his curly hair or to match the curly shape on the front of the B. Okay, so that's what it'll mean going through. And of course, he can have superposition, but now it's a superposition of 6 possible basis states, all of which have prefactors, which ultimately end up being normalized so that both of them are systems that are sensible from a probability perspective. Okay, so where we would be here is that Alice has a 2D complex vector space, and Bob has something a bit more hard to visualize. He has a 6-dimensional complex vector space for his system. If we want to put these together and consider them as one entity to handle mathematically, what we do is a thing called a tensor product. And you'll notice in this lecture, I'm making a subtle shift in my wording here from Hilbert spaces to state spaces. Ultimately, they're the same thing. What I'm starting to do here is get you across from the idea of, sort of formal introductory quantum mechanics texts, which always call these generally Hilbert spaces, through to sort of, if you start reading quantum mechanics books, they tend to talk more about state spaces. And this is really just a vector space that represents the state of the particle, okay? So we can call the state space for Alice's system space A. This is really just taking a 2D complex vector space and giving it a name. And we can do it for Bob's as well. We can call SB, and that'll be a state space for Bob's system. And then we can make a combined system, which is just a tensor product. Tensor product is really just a sophisticated word for saying that we're multiplying two tensors together. And a tensor is really just a geometric object that describes linear relations between vectors, scalars, and other tensors. It's kind of a catch-all for geometric objects of linear algebra from the perspective of what we're doing here. Okay, so what we can do is basically say, well, Alice's state space is a tensor and Bob's state space is a tensor, and we can multiply two tensors to get a new tensor, which is kind of the combined state space of the two systems. Okay, the two base state systems that we have are orthonormal and complete, in the sense that for Alice's, there's a basis that's orthonormal and covers every single possible vector in the system. Completeness, the same idea we had in the last lecture. And same for Bob's system, except it's a bigger system. When we combine these two things together, what we get is like a combined system state space. And now we have to look at all the possible combinations of the system, right? If you imagine that Alice has a coin and Bob has a dice, and we want the measurable outcomes of the combined thing would be Alice gets a heads and Bob gets a 1, or Alice gets a heads and Bob gets a 2, Alice gets a heads and Bob gets a 3 through to 6. Or Alice gets tails 1, tails 2, tails 3 through to 6, right? So there's 12 possible outcomes for the measurement of the system. And that means that we basically need a 12-dimensional complex vector space in order to handle that system. Okay, so we're taking 2 dimensions times 6 dimension is 12-dimensional vector space. Visualization here is basically impossible. So now we have a space, combined space, that's spanned by 12 basis vectors. They're usually written in a form like this. In our particular case, that would be H4, or it might be up, down, 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 up, if we got 2 spins combined in a system. And they're really just the products of the tensor products of the basis vectors for the 2 independent systems. And in this new combined space, what we can do is make superpositions. So we can make, for example, a superposition state that's, some amount of the outcome heads 1, some amount of the outcome tails 1, some amount of the outcome heads 2, so on all the way through. And then, we could do a measurement, collapse that state, and so forth. Okay, so we're really now just extending quantum mechanics up into combining systems together. For the rest of this lecture, I want to look at classical correlation. And the reason for that is that when you get to quantum entanglement, you very quickly realize that it's nothing more special than taking the quantum mechanical aspects we already have for a single spin and really just combining it with classical correlation from probability theory. And it enables you to very quickly demystify this whole topic. In order to get into this, I need to introduce another one of our quantum characters, which is Charlie. So Charlie's job is some mix of referee and preparer of experiments for anything that we do in sort of quantum information science. So the way we have this is Alice and Bob basically are owners of our 2 quantum spin systems. They will hold on to them. They may know something, they may not know something. They will do measurements when measurements have to be made. Charlie's job is basically to prepare things in advance to give to Alice and Bob. So imagine we want to, say, prepare a spin as a spin up and another spin as a spin down. Charlie does that by some series of measurements that Alice and Bob don't know about, hand them the bits, and then Alice and Bob do the measurements in those cases. Okay. we're going to use Charlie on our way through our classical correlations as well. And just for a bit of trivia here, there are other characters. So for example, if you do quantum cryptography, there's a character called Eve, and Eve's job is basically to try and hack or gain access to encrypted signals being sent between parties in sort of via quantum systems. Okay, so back to Charlie. Charlie's going to take 2 coins. At the moment, we want them to be classical coins, right? And we don't really care about the heads or tails of them. We just care that one is a coin, one is a Dogecoin, and one is a penny, for example. And we're going to do this classical correlation experiment entirely along the lines of which coin is which, okay? And the reason we're going to do that is because Charlie's going to take those 2 coins. He's going to put them into a pair of identical envelopes in such a way that he can hand them to Alice and Bob without them having any idea which coin is on the inside. And then we're going to look at what happens as part of an experiment of Alice and Bob working through what is in their envelope. So let's do that. We take a Dogecoin in one envelope, a penny in the other. The envelopes are identical. We give one to Alice, we give one to Bob, and we put them on either side of a wall so that one can't see what the other one's got, and so forth. Okay, I'm going to need some paper to write here. And what we're going to do is repeat this experiment n times. So let's just go through and just think our way through what would happen in this experiment. We have Alice on the left here, and we have Bob on the right, right? Wall down the middle. And imagine that what we've done is given them instructions that at a particular time, Alice, I want you to open your envelope. At a particular time, Bob, I want you to open your envelope. And those are 2 at the same time. And what we do is we give them a stack of envelopes, or Charlie just keeps feeding them through a slot, right? So imagine at time 1 minute, they both open their envelope. At time 2 minutes, they get a new envelope. At time 3 minutes, they both open them. And then they just keep doing this again and again and again, right? And what we're going to do to make this mathematical is if they happen to get a penny, we'll give it a +1 because it's real money and it's got value to it. And if they happen to get a Dogecoin, then we'll give it a -1 because Dogecoin, even though it's on the way to the moon, has essentially no value in real terms. So let's go through and do this. Alice opens her envelope, and what she finds is she's got a penny. So that would be a +1. Now we know that there's the way this has been set up, Charlie's got a Dogecoin and a penny, and so if Alice has got a penny, then Bob must have a Dogecoin. He opens his envelope, he has a Dogecoin. It's a -1. Okay, first episode of the experiment. Go through and we do the second one. Alice opens her envelope. This time she has a Dogecoin. It's -1. Bob opens his. It has to be a +1. There's no other option, right? Because at any particular point, there's one of each coin being delivered by Charlie. We go through and we do this again and again, right? So every time, this time Alice might get a -1, Bob might get a +1. Alice might get another -1, Bob will get a +1. On the 5th attempt, it might be a +1 and a -1 in here. And then we would just go through and we could do this 1,000 times. So we get to the point where you can obviously see what's going to happen here. Alice is going to have a stack of pennies that's the same height as the stack of Dogecoins, because 50% of the time she's getting pennies and 50% of the time she's getting Dogecoins. And on the opposite side of the wall, Bob also has a stack of pennies and Dogecoins that's the same height, because 50% of the time he's getting a penny and 50% of the time he's getting a Dogecoin, right? This makes perfect sense. You could go down to the higher year lab and you could enact this exact experiment there. There's nothing weird about it. There's nothing spooky. It's just correlation in probability, right? So there's two things that we find in here. On average, Alice and Bob will both get as many pennies as Dogecoins, right? Mathematically, what that means is that the average sigma that Alice will get is 0. And if we go down to the bottom here and we basically just added all of these numbers that we get down here, it'll be +1, -1, +1, -1 all the way through, and it'd eventually be 0. And same for Bob, it would be 0 as well. Okay, so this would be expectation value of A. Okay, all we're just saying is what would Alice expect to get on average? She would expect to get 0 because all the +1s would cancel the -1s, and same for Bob. The interesting thing is if they record their results, and they're on separate sides of a wall, they record their results sequentially and they compare them on return, right? One thing that you'll spot in there is that every time Alice gets a +1, Bob gets a -1. And what we could do here is actually write the product sigma A, sigma B over here in a separate column for every single instance of this experiment. So +1 times -1 is -1. -1 times +1 is -1. -1 times +1 is -1. And so you get the idea. This goes all the way down with -1s all the way down this whole experiment. And so if you average those out, the average sigma A, sigma B down here will be -1. And notably, it's not 0. Okay? What we're seeing here is basically just a thing called correlation, right? We set up the experiment in such a way that the outcome of one of the measurements will be reflected in the outcome of the measurement in the other measurement, and sure enough, that's what we get. And this is what we call here a perfect correlation, in the sense that for every time we do the experiment, we get a relationship, a fixed relationship in the pair that the series are related to. Okay. What we like to do in physics all the time is to try and quantify things, right? So we could come up with a quantity here that we call a statistical correlation. If you go on long enough in physics, you'll start to calculate things like correlation functions and so forth that are basically connected to this idea. And it's this thing here that we call chi. What we basically do is we take the difference between the expectation value of the combined result minus the individual expectation values of the individual results, and we use that to tell us a measure of how correlated the outcomes are. Okay, so in this particular case, we would have -1 minus 0 and 0. So this would be -1. A chi of -1 means we have a perfect correlation. And if that chi is 0 in here, if they're not correlated to each other, we'll get a 0. I'll show that in a moment when we go through and do another experiment where we break the correlation in here. And one thing to bear in mind is it is possible to get chi between 0 and 1 and -1 here. It's what we would call a partial correlation, and we'll look at that as we go forward. There's one other really interesting feature of correlation that I want to get to in here, which is if you consider the probability distribution for the two outcomes. If there's no correlation between the outcomes of two experiments, then the probability of the combined outcome can be factorized into the probabilities of the individual outcomes. I'll show this in a minute for an example of an uncorrelated version of the experiment we just did. The important thing in this is that if there is a correlation, then the probability of the combined result cannot be broken down or factorized into the probabilities of the individual measurements. Okay, there's something more that determines the probability of the combined result here compared to the probability of independent measurements, and this is this thing that we call correlation. Okay, so let me just demonstrate this really quickly by cloning Charlie. So what we're going to do is set up a new experiment here. We're going to have Charlie A and Charlie B, or we could have the same Charlie doing this, just doing what he does. So let's imagine we have Alice and Bob where they were on opposite sides of a wall with a slot. They get delivered envelopes. The way Charlie does this experiment is he takes a Dogecoin and a penny and he puts them in two envelopes. He takes one of the envelopes and gives it to Alice. He takes the other envelope and he throws it in the garbage bin. Then what he does is he takes a penny and a Dogecoin, puts them in two envelopes, passes one through the slot to Bob and throws the other one in the garbage bin. And so what we'll know will happen here is that Alice's outcome of the measurement now is entirely independent of the outcome of Bob's measurement, right? Let's go through and have a look at this as a second example. Well, Alice, we got Bob. And so in the first instance, Alice might say get a Dogecoin, so it'd be a -1. And of course, Bob can get either as well. There's no correlation between the two anymore, so he might get a -1 as well. Then Alice would do it again. She might get a -1, get a second Dogecoin. Charlie will do the experiment. This time he gets a penny. So you got a +1, right? Go through and do it again. This time we might get a +1 and a +1. This time on the fourth attempt, we might get a +1 and a -1, and so forth. You could go on doing this forever and ever and ever, all the way down, right? Let's have a look at what happens in here when we tally this all up. For Alice, she's still getting -1s and +1s with 50-50% probability, right? So in the end, if you add all of that up, the expectation value for that outcome is going to be 0. If you do the same thing for Bob, he's now going to get the same result. And the interesting thing that happens here is if you now work out this sigma A, sigma B, because -1 times -1 is +1, -1 times +1 is -1, +1 plus 1 is +1, and +1 minus 1 is -1, and work your way down here. Now you can see this sigma A, sigma B is some 50-50 mix of +1s and -1s, and when you add that, you get down to the bottom and you get 0. And so if we go back to our statistical correlation for a second, you end up with 0 minus 0, 0, you get a correlation of 0 in here, okay? So let's just consider this idea of the probabilities being factorizable here for a moment. So we're going to do the two independent Charlie's version first. So basically what we're going to do is go back to this experiment here. We know that the probability of +1 for Alice is 0.5, okay? 50% Dogecoin, 50% penny. And we know that the probability of a +1 for Bob is also 0.5. And we can just put an A and a B in here just to denote these two things. We can then think about what the probability of a pair of pennies is, right? So this would be a probability of the pair experiment. And we want to get a +1 and a +1. And as we saw up above, that happens roughly 1 in 4 times, right? So this will be 1 on 4 or 0.25. And you'll realize here that if we take probability of A +1 times probability of B +1, what we will get here is 0.5 times 0.5, and of course that's 0.25, which is equal to that thing. Okay, so basically the probability in that particular case is factorizable into the two halves. Let me go back to the original version. For a second. Let me pop back through the slides to find, there it is there. There it is there. In this particular case, we know that the probability of Alice getting a +1 is 1/2, and the probability of Alice getting a -1 is also 1/2. The probability of Bob getting a +1 is 1/2, and the probability of Bob getting a -1 is also 1/2. Okay, they're going to get one or the other. The interesting thing in here is if we consider the probabilities for the combined states, probability of A, B of +1 and +1 is 0. It's an event that we never see because of the correlation, right? If we consider the probability of a +1 and a -1, you'll remember that we got 1/2 for that, right? 50% of the time we saw Alice with a penny and Bob with a Dogecoin. The probability of A, B -1 +1 is 1/2. Same argument. And the probability A, B of -1 -1 is also 0 because you'll remember the correlation means that they never get both a Dogecoin at the same time. And so what you'll notice here is that none of these PAB values can be written as a product of PA and PB. because the product PA/PB would be a half times a half is 0.25, and none of those values is 0.25. They're either a half or zero. Okay, so this is a special feature of correlated systems that if the system's uncorrelated, you can factorize the probabilities and treat them as independent systems, entirely independent systems. And if there's correlation built in, then you can no longer treat those systems separately. You kind of have to deal with them as a combined whole, and you can't factorize that probability out. This is a good point to stop and take a break. And in the second half, we'll come back and look at the quantum mechanical equivalent of this sort of experiment.